Okay, I'm trying to follow the instructions of the organizer and give a talk that actually asks more questions than I answer. And the subject of the talk is which physical processes control massive galaxy formation. And I'm going to try and compare and contrast the sort of theoretical assumptions that are made in many semi-analytic models and other models of galaxy formation, and ask what observational evidence actually exists for some of these modeling assumptions. So let's start off with this flowchart, which Gabriella already showed in her talk. As you know, if you want to understand the formation of all galaxies, let alone massive galaxies, there are a lot of physical processes that you have to be able to understand. So this slide came from a paper by Cole et al. In 2000. And one of the input at the top here is the cosmological model, the power spectrum, value of omega, and so on. And then the issue about how do dark matter halos form and build up via the process of merging and so on. And what has happened since the year 2000 is that we now believe that these first two blocks are perhaps under control, or under control enough for the purposes of understanding galaxies. And what we have to now get under control is all this mess here at the bottom. So what I want to do in this talk is to go step by step through some of these processes and ask and compare what we do in the theoretical models with what we know from observations. So I would say that the most fundamental process in galaxy formation, and one that most people haven't talked about so far in this conference, is cooling of gas. So we know that galaxies form when gas reaches high enough over densities to cool and to condense at the centers of dark matter halos. That's what we learned in our galaxy formation primary course. And as Sandy said, since the 1970s, we've had this paradigm that there are several regimes of gas cooling. In regime 1, the cooling time of the gas in the halo is short compared to the assembly time of the halo. Another way to say this is that the cooling radius lies outside the virial radius. And gas accretion is regulated by the infall of new material onto the galaxy. This is the regime which people who now talk about this process refer to as so-called cold accretion. In regime 2, the cooling time of the gas in the halo is long. The cooling radius lies inside the virial radius of the halo. A quasi-static atmosphere of hot gas forms, and the cooling rate is regulated by radiative losses near the cooling radius. This is the so-called cooling flow regime. And I'll argue that direct observational evidence at the moment for gas with cooling in either regime 1 or regime 2 is rather elusive. Unfortunately, I think it's one of the problems in our field. Now, regime 2 is being extremely problematic when it comes to looking for hot gas in the X-rays around halos. One of the papers in this field is this paper by Benson et al. In 2000, which they took deep rosette pointings of a sample of 3 of the largest spiral galaxies in the local neighborhood. And they chose spiral galaxies because these are galaxies where stars are forming, where they hoped that there would be a detection of gas that would actually be cooling and fueling the star formation. These 3 galaxies have circular velocities in the range of 277 to 358 kilometers a second. So they are hoped that they would really be in massive halos where you could get a good detection. And from the models that they did, they predicted that the estimate of the X-ray luminosity emitted in the cooling region should be of order of 10 to the 42 ergs per second. But these rosette observations showed clearly upper limits that were up to 2 orders of magnitude below this, down to about 10 to the 40 or so, or even 10 to the 39 ergs per second. Thus, they concluded that the true luminosity lies well below the theoretical prediction. And they said, well, this is only 3 galaxies. A larger data set is needed to explore this important problem further. But there have, since this paper, been almost no papers in the literature about this. There was one this year, a claimed detection of NGC 5746 by Christian et al. But some X-ray colleagues that I've talked to question the analysis of this data. So I don't know if there are any real detected X-ray emission around large spiral galaxies.
Theoretical calculation, how was that made?
Simon, do you want to comment since you did that?
There's no calculation. It's you assume that there's some fraction of gas that follows approximately the dark matter distribution, and then you calculate the cooling rate predicted that's true.
It's making noise. Just come over here for a second.
Give me an extra minute. Okay, sir.
Can you take your deep take it? I'll give you extra time, don't worry. There. I just put them on again.
Okay.
You want to just do it really quick?
I'm having interference, apparently.
Yeah, it was scratching from the, Okay.
Okay. So in clusters, you can see the X-rays, but as we know from the new era of spectroscopy from XMM and Chandra, that the gas is apparently not cooling before below 1 keV. And the solution that most X-ray astronomers seem to favor these days is that the radio AGN that are seen to be heating the gas do provide enough energy to terminate the cooling in these rich clusters. But the question, I think, for the purposes of people in this room, is to ask, is this, if this operates in clusters, is this the universal solution for why we don't see hot gas around galaxies? Does this form of feedback apply in all massive halos? And I think this is an open question, and the answer is very unclear. Now, what about regime 1, the regime where cold gas is cooling very rapidly, and one should see inflow, one should see accretion, which is regulated by inflow. Now, this has been studied recently in SPH simulations. Sandy showed work by Birnbaum and Deckel. This is work by the group of Keres and Katz and Weinberg, who've also looked at this cold accretion process in SPH simulations. And I've stolen the slide from David Weinberg. It's a basic summary of the results from these studies, is that basically the cold accretion follows a filamentary structure, and it dominates in the regime of low mass halos at the present day. So the quoted galaxy mass is around 2 times 10 to the 10 solar masses, and a halo mass of around 5 times 10 to the 11, where this transition from hot to cold accretion regimes is affected by parameters such as the UV background, and also, very importantly, by the metallicity. And then in the transition regime, you can get cold and hot modes which coexist. Now, the observational problem for being able to study this is that basically we're not able to detect H1 in these small lumps coming into galaxies with present radio telescopes. This is something that we really need the square kilometer array in order to see cold gas falling onto galaxies. But in the meantime, I think it's rather interesting that perhaps certain wavelengths, in particular UV, may give us a small but indirect but interesting glimpse into this sort of cold accretion mode. So Richard Ellis in his talk introduced the GALAX satellite, which is the UV imaging satellite, which was launched in 2003. And some of the results have just been coming out in papers in the recent year or two. This is from an early press release in 2005. GALAX, in quotes, discovers invisible spiral arms around a galaxy previously believed to be an early type. So this is something, a well-known nearby galaxy, which had been classified by all the famous classifiers as an early type S0 SA galaxy. And when GALAX looked at it, it saw extended structures, in fact, spiral arms of UV radiation extending much further from the body of the galaxy that had previously been known. And this is kind of a generic thing that GALAX has been able to see, and it's very easy to understand because, number one, because the background, the sky background is very low, and the UV offers greatly enhanced sensitivity to low rates of residual star formation in galaxies in the absence of dust. That's very important, that as soon as there's some dust, that UV gets absorbed. You don't see it anymore, and this favors really the outskirts of galaxies, which are chemically uninvolved. So here's a plot that in the absence of dust, this is on the y-axis, it shows the fraction of the mass in stars which are formed in the last gigayear as a function of an optical color. G minus R is a function of the UV minus optical color and UV minus R. And what you see is that the optical colors basically saturate at residual star formation levels of a few percent or less. You have no more sensitivity to that last bit of star formation. But in the UV, you're sensitive right down to 10 to the 3, 10 to the minus 4% of the stars formed in the last gigayear. So the surprise from GALAX is that massive bulge-dominated galaxies appear to exhibit much more scatter in their UV optical colors than in their normal optical colors. So here is a color magnitude diagram, or a color sigma diagram, of the same set of galaxies drawn from the Sloan Digital Sky Survey. Here's the G minus R versus sigma plot, and here's the NUV minus R versus sigma plot. And particularly at somewhat lower values of the velocity dispersion, the scatter really blows up. And what's being done here is that the points have been color-coded according to the emission line properties of the galaxies. And in fact, all these galaxies color-coded in red here, which make up the bulk of the blue NUV population, turn out to be AGN. So that was also a surprise. So we get a much bigger scatter in the UV colors, and a lot of them are classified as AGN. But when you go in and look at some of these more nearby systems where you do have enough resolution from the galaxy to be able to see the UV light, what you discover is that UV light is coming from extended structures. This doesn't show up very well, unfortunately, but the UV light is always coming from an extended disk component. So these postage stamps are physical radius of about 100 kiloparsecs on the side, and in some of these ones you can see better, the disk fills up actually most of the diameter of this postage stamp. So these are really extended UV bright objects that you basically just don't pick up in the optical. So the question is, what is the relation between the UV bright outer disk and the AGN? Well, we have a rather nice window of galaxies in the redshift range of around 0.05, where we can probe the stellar populations at different radii using these different indicators. So basically the outer stellar population, the stellar population of the whole galaxy out to, as I showed you, 40, 50 kiloparsecs, is probed by this color NUV minus R. The interstellar population is probed by the SDSS fiber, which spans typically a diameter of about 3 kiloparsecs that really probes the bulge region. And we can use the spectral indicators such as D4000. And the black hole accretion rate relative to Eddington we can get from the emission lines and the AGN indicators. So what you find from looking at the correlations between all these different indicators is some indicators correlate with a sort of interesting triangular shape, and some indicators correlate much more tightly than that. And if you think about it, what these triangular correlations actually mean is necessary but not sufficient. So what we find from these correlations is that this UV bright disk, this outer stellar population, is necessary but not sufficient condition for bulge and black hole growth. So in other words, if you find a strong AGN, if you find a bulge which has a blue stellar population, then you always find this blue outer component, this UV bright component. But if you find this UV bright component, you don't always find the reverse. It's necessary but not sufficient. But on the other hand, star formation and presumably gas in the bulge is necessary and sufficient condition for black hole growth, as shown by this much tighter correlation here between the accretion rate onto the black hole and the stellar population within the fiber. Okay, so let me now move on to the second process, which is star formation. I don't have very many slides here because I think our knowledge about star formation globally in galaxies is still rooted in this classic plot, the Schmidt-Kennicut law. So this is our bedrock in the local universe, and this is what all simulators, modelers do. They calibrate their multi-phase ISM model, their semi-analytic model, on this Kennicut relation. And the question we have is, what about at high redshifts? Do we still apply this? In fact, in recent papers, people have just gone ahead and assumed it. But unfortunately, empirically, in order to make progress, again, we need information about gas to understand this fundamental issue, and we don't have it. The other question is Kenniket phase 2. This is Kenniket, the zeroth order relation. The second relation is that star formation thresholds exist, that in the optical you see sharp outer radii of the disks, and you can interpret this at the point at which the disks are going basically stable against gravitational instabilities from the arguments of Toomer. But what's, again, another GALAX result which has emerged is a new analysis recently on AstroPH by Boissy et al., which seems to indicate that in some of these extreme UV disks that you can actually see star formation in the UV going out well beyond this so-called threshold radius. So this is the Kenniket 98 points for the sample they studied, and this is the threshold radius calculated by Kenniket, and at least as found by GALAX, that the star formation continues out to radii well beyond where the optical disks seem to cut off. Supernova feedback. Maybe people here think that this process is not relevant to massive galaxies because supernova feedback perhaps not powerful enough to eject gas and metals out of 4L star ellipticals, but nevertheless in the sort of scheme of the models it does play an important role, because the material which is ejected out of low mass galaxies influences the metallicity of the gas, of the intercluster medium, the intergalactic medium, and then will influence things like the cooling rate. And the cooling rates then in turn will influence the issues about overcooling and how much mass gets transformed into stars in the most massive galaxies. So everything is interconnected. So the hope we have is that we can apply some of the lessons we've learned from studying feedback from starburst galaxies, for example, from the beautiful work by Crystal Martin and Tim Heckman, and combine that with demographics, for example, the mass-metallicity relation, in order to infer how many metals have been ejected from galaxies into the intergalactic medium. So in the paper by Tremonti, one of the issues that we face in trying to interpret these mass-metallicity relations is to understand whether this relation arises simply because metals have been ejected out of the galaxy, or simply because the processing of gas into stars has been less complete in low-mass galaxies. And the way you can distinguish that is to use information, once again, about the gas. If you have diagnostics of metallicity and you have measurements of gas mass, then you can infer this quantity called the effective yield. And if this effective yield falls below the value that you would predict from the simple closed box model, then you can say with some confidence that metals have indeed been ejected. And in the paper by Tremonti, she combined real gas measurements of dwarf galaxies with indirect gas measurements inferred from H-alpha luminosities of the Sloan galaxies, and claimed that indeed there was evidence that the effective yields were going down at lower masses. This is still under some debate. A recent paper by Lee et al. They have a different sample of dwarf galaxies and claim to find higher values of effective yield and a bigger sample, basically a bigger scatter. And the roadblock, once again, is information about total gas mass for complete samples of galaxies. Okay. 5 minutes? 10 minutes, okay. So, 8 minutes. Okay, it's going down. I won't ask you again.
6.
So let me come on to the subject of bulges and black holes. So this has been a hot topic in recent years, and I think it's summarized very nicely in this picture here, which has maybe become the paradigm. Once you have a good movie, you have a paradigm for how things form. So the question I'm asking here is, does the bulk of bulge and black hole growth in the universe occur during major mergers? In other words, the subtitle is this movie correct? So the comment I'd like to make here is that once again, you can correct me if I'm wrong at high redshifts, but at low redshifts, I think it's true to say that it's been rather hard to find direct observational evidence of a link between optical AGN activity and major mergers. So many people have looked at this from different samples and concluded that what evidence there was rather marginal. And we ourselves did this in the Sloan with a huge sample of 80,000 AGN. And the way we did this was simply to go and count galaxies in the photometric sample as a function of projected radius, subtract out the background, which you can do very nicely, and ask whether there was any excess in pairs or companions relative to control samples of non-AGN that were very closely matched in terms of physical properties such as stellar mass, bulge velocity dispersion, and even stellar population in this case. And what we did find, and we found marginal evidence of some excess of companions around, in particular, the highest luminosity AGN, but it's really a small effect. It's not as though every powerful AGN has one excess companion that you can point to as doing the trigger. It's more like 1% of AGN have this excess companion.
How do you see that in that figure? What do you look at?
So this is basically the average count around control samples. So this is just n as a function of radius, and this is the AGN, the red line, and this is basically the error bar is this yellow region over here. So you can just look at the difference here. It's about a 1% effect. In fact, when you look at correlations, if you look at the correlation function or the cross-correlation function between AGN and between surrounding galaxies, the most striking results that you get is not an increase in companions, actually deficiency of neighbors around the AGN, and that occurs on somewhat larger scales between 100 kiloparsec and 1 megaparsec. So this is basically...
Prove it though, because they've all been used up in the merger.
Okay, so that it could be that the AGN is only triggered after it's been swallowed, and that's why we don't see this companion. So I'm just presenting the observational results. So the way we chose to interpret it is through a different hypothesis. So we saw this basic one halo term of deficiency relative to the control sample, and at least in our interpretation, we showed that this result could be consistent with a model in which AGN are just preferentially located at the centers of their own dark matter halos. If you say that AGN don't like to be in satellite galaxies in large groups and clusters, they like to be their central galaxies, and we made a model of this using the Millennium Run simulations, and actually could reproduce this feature quite nicely. And we thought this was consistent with the idea that gas cooling and cold gas accretion could play a vital role in maintaining ongoing AGN activity. So I would put it forward to you, and maybe it's a point for discussion, is that a violent trigger, for example, a major merger, at least as far as I see it in the local universe, may not be required in order to produce substantial black hole growth. Maybe there's a more quieter mechanism that does it. Okay, on the subject of AGN, another question: are there indeed separate and distinct quasar and radio modes of AGN activity? And if so, which mode has more influence on the evolution of massive galaxies? So I guess this will be a theme tomorrow when we have Darren Croton, who says that radio AGN feedback is instrumental in explaining color by modality. And we have Philip Hopkins, who in many papers says that the quasar mode is most important. So what do the observations say? Well, I think in the local universe we can show that, yes, indeed, it is true that radio and optical AGN activity are independent, separate physical phenomena. And that's shown in recent work by Philip Best. And the way he's done that is to make this plot here of the fraction of galaxies that are radio loud AGN as a function of the stellar mass. And what you can see, this generic result, that the fraction of radio loud AGN is a very strongly increasing function of stellar mass. Basically, by the time you get up to most massive galaxies in the universe, good fraction of them, 30–40%, are on all the time as radio sources. This is a duty cycle of almost 1. So he made this plot for all galaxies, and he made this plot for emission line AGN. And to first order, you see basically no difference. So the fraction of being radio loud AGN doesn't care whether or not it's an optical AGN. So the probability that a galaxy is radio loud is a strongly increasing function of black hole mass and of stellar mass. However, the other result that came out of Phillips' work is that the distribution of radial luminosities is independent of black hole mass. So if you construct this function, which is the bivariate radial luminosity black hole mass function, you see, so this is the distribution of radio power in different bins of black hole mass. You see that all these functions have roughly the same shape, and indeed you could collapse them vertically and show that within the error bars they can be fit by this double power law model. So apparently, even though the fraction of time that a black hole is on as a radio AGN is going up with mass, the power of its radio jets, or at least the luminosity of its radio jets, does not depend on black hole mass. So we've extended this work now to a sample of 625 brightest group and cluster galaxies from the SDSS. This is the work of Anja van der Linden, who's a PhD student at MPA. This is also based on the C4 sample, but she's done a lot of extra work to make sure that we are identifying the correct brightest cluster galaxy, which C4 doesn't do. And basically what you find is that the fraction of radio loud, I've got 2 more slides, radio loud AGN is significantly boosted in central group and cluster galaxies relative to the field galaxies of the same mass. So this is the relation for all galaxies, with the percentage of galaxies that are radio loud going up strong as a function of mass. And if you confine the results to brightest cluster galaxies, you can see a significant boosting, and particularly at the low masses. However, the distribution of radial luminosities is always the same. So Philip has attempted to put this together by taking these observational results in order to compute the time average heating rate associated with radio AGN activity as a function of dark matter halo mass. We have velocity dispersions, and ask whether this can balance radiative losses from cooling in gas. So basically we have this from the radio luminosity function and the information about central galaxies. And the answer we get, which is described in the paper, is that you cannot simultaneously balance cooling in dark matter halos of all masses. If it works in clusters, the groups will be overheated. And conversely, if it works in groups, you will not manage to balance it in clusters. So maybe this is telling us something. Maybe this is telling us why we don't see X-ray emission in groups and low mass halos, that basically it has the radio jets have kind of overcompensated, and they have kind of blown everything away, and most of the time we're actually not seeing X-ray emission from them. So I'm going to leave you with this question. If we like radio AGN and we think there's something to them at low redshifts in terms of heating of gas, what is going on at high redshifts? There are lots of radio AGN in the high redshift universe, but they're much more complicated beasts than in the low redshift universe. I point you to 2 recent papers, one by Nesvadba claiming evidence for huge amounts of outflows in powerful radio galaxies, another paper by Miley et al. Saying that radio galaxies are made by inflow of huge numbers of clumps. So what I think there's something to be understood here.
Thank you for the very objective summary of all of our theoretical thoughts. You ended up being somewhat negative on the merger as a fueling of AGNs and looking for a more conventional hypothesis. And there's one very, very conventional hypothesis which I've explored with Luca Ciotti, and that is that it's just the gas emitted in planetary nebulae in the systems, the recycled gas. And that seems to work fairly nicely, and it would say that it would happen less often in clusters where that gas gets swept out than in isolated field galaxies. So that's a potential candidate for what is actually doing the refueling.
Sure.
I'm just wondering, on your plots of radio loud fraction versus stellar mass, what happens when you split the galaxies by red and blue, optical red and blue? Do you get differences there?
Essentially, yeah, there's basically no dependence on red and blue. So what we concluded was that the main driver was basically black hole and stellar mass, and so we then looked for residuals away from that as a function of optical aging activity and as a function of stellar population age. And the zeroth order answer is that there isn't any dependence. It really seems to be independent of star formation and independent of optical aging activity. Doesn't know about it.
So just all right. So just a comment, which is, I think you made this point implicitly when you were talking about mergers as a fueling mode at low versus high redshift. But I think few of the merger proponents, myself included, would argue that you really need them for low redshift. I mean, it's important to remember that L star of the quasar luminosity function locally is less than Seifert luminosities. So you don't have very bright things. But that having been said, while it's true that the central galaxy argument would be a prediction if it was gas cooling from the halo onto it, that's also where you'd have mergers acting most efficiently.
Yeah.
So I don't know that, I mean, can you rule out other models like, I mean, some people have talked about harassment or flybys and minor interactions. Is that possible to rule out from this?
Well, the test is what I showed you, simple counts. I mean, if you want to, I think if you want to go to the next order, you'll have to do what I'm sure we'll hear some talks by people in this room. Look for actual deformations in the images of the galaxies. Look for tidal features and so on, and ask whether that's correlated with AGN activity. So I'm hoping to hear some results from that. But all I'm saying is that the people who have looked so far, as far as I know, haven't yet been able to show convincingly that. And I wrote a paper about mergers triggering AGN, so I'd like to believe that it's happening at some point. But
we have time for one more question. Those outer disks, the outer spiral arms that were detected in GALAX are very interesting. I think it would be fair to say that Annette Ferguson also found similar things by looking at H alpha far out, which is another sensitive way of doing it, and that there's also some results that suggest that not all spiral disks are actually truncated. But what I was curious about is whether you're adducing this as evidence of cold accretion, or if it's just H1 disks that go very far out.
that's a good question. Unfortunately, yeah. The fact that the disks go very far out, and the fact that when people have looked at them in detail, that their metallicities are dropping to hundredths of solar and so on, is indication to me that perhaps this is the this is material which is being accreted most recently. And from a theoretical point of view, we believe that disks assemble late through gas, which is basically losing angular momentum and becoming centrifugally supported in the halo. So it's a kind of a theorist's wish that, that perhaps by studying these GALAX disks that we're looking at the last episode of accretion. But I agree that this is still an indirect way of studying it.
All right, we're going to stop for now and have a 5-minute break. Let's thank Guinevere again. It's 3:10 right now. Let's be back here at 3:15, and we'll go on just a bit of a